Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the third lecture of fourth week, and we'll start off with this last topic, and very small topic in essence, not very difficult if you have already comprehended the cylindrical coordinate system, the spherical coordinate system, and the rectangular Cartesian coordinate system which we had already discussed earlier. So this is just a supplementary topic that if which has got the main title conversion of a vector, and we have got 4 cases in it. That if we have a vector in a particular coordinate system, how to convert that vector from one coordinate system to another coordinate system. So we'll take this first example, that if we have already a vector which is in Cartesian coordinate, how to convert that vector from Cartesian to cylindrical coordinate system. So let's say we have got a vector A which is given in Cartesian coordinate system. This is given, and I am representing the given vector as equation number 1. So I have appended a subscript r just to emphasize that this is a vector which is in Cartesian coordinate system, and what we need is a vector which is in cylindrical coordinate system, and we have got the 3 components of cylindrical coordinate system: rho component, phi component, and z component. This is the one which is required, and I have represented this vector which is required by equation 2. So there is a very important point that you must know, that whenever you are asked to convert a vector from one coordinate system to another coordinate system, you will not be given the vector alone. You must know the point at which the tail of the given vector lies. So the location of the tail of vector A must be known in either Cartesian coordinate system or cylindrical coordinate system. So the location of the tail of AR, actually AR is the given vector, so the tail of the given vector, the point at which the tail is lying, must be known either in Cartesian coordinate system or cylindrical coordinate system. It does not matter. Let's say the tail of the vector is at point P, and this is the given point, and the coordinates are mentioned in Cartesian coordinate system, that is x, y, z is given. If that is the case, then we will evaluate or convert this point into its equivalent cylindrical coordinate system representation, in which the same point P will be represented by rho, phi, and z. We will find that out using the formula which we discussed earlier while we were at the end of the cylindrical coordinate system. The very last subtopic which we discussed there was the conversion of a point from cylindrical to rectangular and back. Okay, so we'll find it out. So if the given point is already in cylindrical coordinate system, so we don't need to do this step number 5. Okay, we don't need to do that because what we need is a point which locates the tail of the given vector, and that point must be in the cylindrical coordinate system. Okay, so if it is already given, so we don't need to perform step number 5. Okay, then after that, once we have found this point, so what it actually means to convert a vector from one coordinate system to another coordinate system, it simply means, in this case for example, it simply means that find out the scalar component a rho, a phi, and az. Okay, just find out a rho, a phi, and az somehow, and replace those values in equation number 2, and you will find what you are looking for. Okay, so we already know, we should have the idea by now that if you want to find a scalar projection, these are the scalar components. If you want to find a scalar projection of any vector in any direction, so what we need to evaluate? We need to evaluate, number one, the unit vector of the direction on which the projection is required, and then we'll have to take the dot product of the given vector, okay, and the unit vector which we just evaluated. For example, a phi a rho a phi az is nothing but the projection of the given vector in the direction of a rho is nothing but the scalar component a rho, okay. Similarly, the scalar component or scalar projection of the given vector ar in the direction of a phi is nothing but the scalar component a phi. And since we know that we had defined a vector z or the z component in the cylindrical coordinate same as we did in the rectangular component, so in that case az is equals to az. So we don't need to evaluate it, okay. So just to repeat that point once more, a rho, a phi and az are the required scalar components. Once we know these values, we can replace those values in equation number 2 and done. We'll get our final answer, okay. And scalar component a rho is nothing but the scalar projection of the given vector ar in the direction of a rho, unit vector a rho, and a phi is nothing but the scalar projection of given vector ar in the direction of unit vector a phi, and az is nothing but az. So if we evaluate this dot product, I am just replacing here in the bracket. What I have replaced is the given vector ar, which is ax plus ay plus az, and this is a dot product or dotted with arrow, okay. So after taking this dot product, it means that we have to take the dot product with respect to each of the rectangular components. So ax dot arrow plus ay dot arrow plus az dot arrow. So this is given in equation number 1. X component, y component and z component all are given already. So how about these quantities, ax dot arrow, ay dot arrow, az dot arrow? We have to refer to this table, which is not very difficult to remember. However, you don't need to remember this because this table will be given in exams as a reference, so you don't need to worry about remembering this table. So ax dot arrow is cos phi, ay dot arrow is sin phi, and az dot arrow is 0 as it should be. Why? Because we know that arrow is a unit vector that lies in the horizontal plane, and az is a unit vector which is perpendicular to the horizontal plane. So both make an angle 90 with respect to each other. In other words, az and arrow both are orthogonal, meaning the angle is 90. So cos of 90 is always 0. We are evaluating dot product, so we know that dot product of orthogonal components is always 0. Okay, so okay, all right, so this is what we have done in step number thus. All right, so simply replace ax dot arrow as cos phi and ay dot arrow as sin phi, and this third term is already 0. Similarly, step number art is explained in the replacement from this table, and this here in this step is given in step number 11, where we had repeated the step number 7 for a phi, this time taking dot product of the given vector with a unit vector a phi, replacing this ar with its original given vector, and then dot with a phi, and then evaluating this, ax multiply by ax dot a phi plus opening the bracket, okay, ay dot a phi plus az dot a phi. Now this is given in equation number 1. These brackets will come from this table, okay. So ax dot a phi is minus sine phi, so we will be left with minus ax sine phi plus ay, and this term is ay dot a phi, which is cos phi, plus this term az dot a phi is 0, and it should be 0. Why? Because we already know that a phi also lies in the horizontal z equals constant plane, and a z is orthogonal to the z equals to constant planes, and az is equals to az, okay. So from where these phi's will come, these phi's will come from here, okay. यहाँ से मिलेगा आपको phi की value. That's the reason why we needed the point of the tail. I hope that this very small topic would be clear to you. So next we'll see the conversion from a vector which is already in cylindrical coordinate system to the one which is in Cartesian coordinate system. So I hope these 12 steps are clear. So we'll see the converse of this case in the next case. So now the second case is that of conversion from a vector which is already in cylindrical coordinate system to Cartesian coordinate system. So this time the vector AC for cylindrical is the one which will be given in terms of a rho, in terms of rho component, phi component, and z component, and this time I have used equation number 1 to represent this, and then AR will be the vector which is required in terms of x, y, and z components. So again, the tail of the vector, given vector C, is required this time, okay. So either in rectangular coordinate system or cylindrical coordinate system. If the tail is given in rectangular coordinate system or Cartesian coordinate system, we will evaluate its equivalent cylindrical coordinate system, and then we will proceed to find this vector AR, and finding this vector AR means that we need the scalar x component, scalar y component, and scalar z component of this vector. And once we'll get these components ax, ay, and az, and then we'll replace that in equation number 2 to find what we are looking for. So the x component of this vector, cylindrical vector, is cylindrical vector A, not cylindrical vector, sorry, vector in cylindrical coordinate system AC. The given vector, the scalar component in the direction of x of the given vector, is the given vector dotted with the unit vector ax, and the y component of the given vector AC is nothing but dot product of AC in the direction of ay, unit vector ay, and az is the same because the z component or the third z coordinate has been defined in the similar fashion both in cylindrical and Cartesian coordinate system. So again, we'll replace this time the given vector which is in the cylindrical coordinate system. Instead of AC, I have to replace a vector in equation number 1 here, dotted with ax. Previously we took the dot with respect to a rho because we needed the rho component. All right, so at that time we were given this, but never mind, it's not very far behind, so I think you can follow it. All right, so the y component is this, okay, given vector dotted with the unit vector ay this term will give us the projection of the given vector in the direction of unit vector, primitive unit vector ay. And if we replace this AC, the given vector, and take the dot product of the whole given vector with respect to ay, so and we can then just take the next steps similarly as we did it previously. In that case, now the terms in the bracket have to be evaluated using this table. So this time a rho dot ax is cos phi. Again, this is the same table as for the case of converting a vector from Cartesian to cylindrical. So this is the same table. So this table will be used for two cases: conversion from Cartesian to cylindrical and cylindrical to Cartesian. I am talking about conversion of vector. We are not talking about conversion of point. Conversion of point has been discussed previously. So we are talking about conversion of a vector from Cartesian to cylindrical or cylindrical to Cartesian. In both cases, we'll use this table. All right. So ax dot a rho dot ax is cos phi. A phi dot ax is minus sin phi. All right. And similarly, a rho dot ay is sin phi, and a phi dot ay is cos phi. Az is az. So remember that you don't have to memorize these formulae. Okay, not this formula, not the formula for the previous case. This is only the procedure that you must follow. Okay, you don't have to memorize these formula. In fact, these are not the standard formula, so you are not supposed to memorize them and use them as a standard formula in solving any numerical. So this is this case or the previous case we discussed, and in both the cases I'm just showing you the procedure to evaluate a vector or convert a vector from one coordinate system to another coordinate system. So you, for every case, you have to follow these steps in exact fashion. Otherwise, these are not the standard formula, so you don't write it, you don't memorize it and just write it and keep referring to these formula. No, that would be wrong. So this was the second case in which the cylindrical coordinate system, vector and cylindrical coordinate system, is converted into Cartesian coordinate system. Next we'll see the conversion of a vector which is given in Cartesian coordinate system and how to convert that into its equivalent spherical coordinate system. Alright, so this is the third case in which a vector is given in Cartesian coordinate system, and we have to find out its equivalent in spherical coordinate system. So again, we are given with the vector in Cartesian coordinate system. This is given and we are representing it as equation number 1, and the one which is required should be in spherical coordinate system with the components ar, a theta and a phi. We are representing that as equation number 2. Again, for this conversion, the tail point of this given unit vector, vector must be known, which is vector ar in this case, and that tail point can be in Cartesian coordinate system or spherical coordinate system. So if the tail point is given in xyz terms or in terms of Cartesian coordinate system, then again step number 5 will force us to find the equivalent point in spherical coordinate system, meaning that we must know the values of r, theta and phi which represent this point in a spherical coordinate system. And the formula for the conversion from a point in Cartesian coordinate system to spherical coordinate system and back has been discussed. Those formulae have been discussed at the very end of the last lecture, in which we were concluding the spherical coordinate system. So once we have found this point P, that is the tail point where the given vector is located. Once we have found that point in spherical coordinates, then we can proceed to find the required vector A subscript S for spherical by finding the scalar components of the required vector, that is AR, A theta and A phi. Okay, so the only unknowns, in other words, the only unknowns in equation number 2 are the scalar components. Once we know these values, we will simply replace those values in equation number 2 and we will find the answer. So the scalar component AR is nothing but the dot product of the given vector A capital R. Okay, so this is small r for spherical coordinate system, the r component of the vector in spherical coordinate system, and this capital AR, A capital R is the given vector. So you should remember this. These are two different things. Okay, so this is the given vector. Take the dot product in the direction of primitive unit vector AR, which belongs to spherical coordinate system. This dot product will give us the projection of given vector A capital R in the direction of primitive unit vector AR, which means that we will find the scalar component A capital A small r. Okay, same as we have been doing in the previous two cases. All right. Similarly, to find A theta, we have to take the dot product of the given vector in the direction of primitive unit vector A theta, and to find the scalar component in the direction of phi, A phi, meaning this scalar component, we just need to take the projection of the given vector in the direction of primitive unit vector A phi. And rest of the mathematics is the same. Now you should expect that this time the terms in the bracket will come out to be different than the ones we were getting in Cartesian to cylindrical and cylindrical to Cartesian conversion. So for that we have got this table, the table of dot product between the primitive unit vectors of Cartesian coordinate system and spherical coordinate system. And remember that you don't need to memorize this table will be given to you, inshallah. So, and also remember that this case or the previous two cases which we have discussed already, these steps are nothing but the steps which you must follow in order to convert a vector from one coordinate system to another coordinate system. All right. I hope from here, using this table, you can find the formula. You can find the last equation of which follows this one. I have not written it over here because I did not have the space left. So in that case, AR, the next step for this step number 7 would be AR is equals to AX dot AR, meaning just replace this bracket by sine theta cos phi plus AY, and then replace this by sine theta sine phi plus AZ dot AR is nothing but cos theta. Similarly, A theta, the next step, the last step for this step number 8 would be A theta equals to AX dot A theta is cos theta cos phi. So instead of this bracket, just write cos theta cos phi plus AY. Instead of this bracket, just write cos theta sine phi, because AY dot A theta is cos theta sine phi plus AZ, and instead of this bracket, just write cos phi, just write minus sine theta. Az dot a theta, az dot a theta, this one. And finally, as the last step of equation of step number 9, you should write a phi is equals to ax. Instead of this bracket, just write minus sine phi, plus ay. Instead of this bracket, just write cos phi, and then this final term would be 0 because az dot a phi is 0, as we already know that az lies in a plane which is perpendicular to horizontal z equals constant plane, and a phi is a unit vector that lies within that horizontal plane, so their dot product must be 0. Okay, so from where would you get the values of theta and phi? You will get those values from this point which you had calculated in step number 5. Okay, so I would stop here, and as an assignment, as a do-it-yourself ungraded assignment, I am asking you now to following the same steps, try to convert the vector, try to solve the fourth case, which is if a vector is given an spherical coordinate system and you have to convert that vector into its equivalent Cartesian coordinate system, what steps would you have to follow in that case? Also remember, you will end up in equations, similar equations, in which in the bracket you will be having ax dot ar dot ax, ar dot ay, ar dot az, a theta dot ax, a theta dot ay, e theta dot az, and similarly a phi dot ax, a phi dot ay, a phi dot az. In that case, you will have to use this table. So in total there are two tables. This table is for vector conversion from Cartesian to spherical and spherical to Cartesian, and the previous table was for two cases, that is vector conversion from Cartesian to cylindrical and cylindrical to Cartesian. There might be another case you might think of, that spherical to cylindrical and cylindrical to spherical, but that case we won't discuss here, because if you want to convert from spherical to cylindrical, so you can just go from spherical to Cartesian, then Cartesian to cylindrical. So there is a way to do that. Or if you want to go from cylindrical to spherical, so you can go in like this: cylindrical to Cartesian, Cartesian to spherical. So this would be the case. Direct conversion would require another table for a conversion of a vector from cylindrical to spherical and spherical to cylindrical, but we are not going in that detail. Okay, so this concludes chapter number 1, the very last topic. Now you should be able to solve all the problems of chapter number 1. Okay, but remember, last very important point, this for conversion of a vector from one coordinate system to another, you have to follow these steps. There is no standard formula for that, as I explained in the previous cases. Okay, from later on we'll start off with electrostatics, and we will actually start our main topic of this course, that is, electrostatics, then magnetostatics, and so on and so forth. Alright, so before leaving this session, I would like to, and starting formally with the electrostatics and magnetostatics, that is the actual field theory, electromagnetic field theory, I want you to remember one thing which we had already discussed in during the lectures of week 1, that whenever there is a field, there is a source of that field, and that there are certain effects of that field which we can sense, and those effects can be vector or they can be scalar. All right, both in the case of electrostatics and magnetostatics. All right, so while we were studying electrostatics and magnetostatics, keeping these tables in mind or at hand would be beneficial, and that will be like, you know, your milestone map, or your you know, achievement map, your progress map, that you'll be able to relate that why we are at this stage, why we are discussing so and so quantities. All right, so this is sort of a mind map, or your progress map for the portion of electrostatics and magnetostatics, and later on when inshallah we'll be able to discuss electromagnetics. In that case, things will be you know, different, and by that time I hope we would be able to cover 8 chapters. All right, so whenever there is a we talk about electrostatics, it means that we are talking about charge which is stationary and constant in magnitude, already discussed. So that is the source. All right, that charge, stationary and constant value charge, is the source. So that charge can be distributed in 0 dimensions, in 1 dimensions, in 2 dimensions, in 3 dimensions. It is not necessary at all that the charge is always a point charge. It can be you know, distributed in a number of ways, but whatever number of in whatever way the charge has been arranged, you can classify that arrangement of the source or of the charge, stationary and constant charge, in terms of these 4 things, 4 categories. Either it is a 0 dimensional arrangement, or 2 dimensional, or 1 dimensional, or 3 dimensional arrangement. So whenever we have got a point charge, it is a 0 dimensional arrangement, because point has not got no dimension. Whenever the charge is distributed linearly, okay, एक लकीर की फॉर्म में, एक लाइन की फॉर्म में charge distributed है, so that charge, that distribution of the source will be classified as the 1 dimensional distribution, or we will call it a line charge. A line charge distribution. A point charge is always quantified as Q, or in the units of coulombs. We all know that. And the line charge, that line charge can be infinite, so we never quantify such arrangement in terms of charge. Rather, we define a charge density, and we call that charge density a line charge density, and we generally represent that as rho L. And if the charge is arranged in a 2-dimensional surface fashion on a surface of any arbitrary shape, but that shape can be classified as a surface. If the charge is arranged in the form of that surface, we'll say that okay, this charge is 2-dimensional, and we will say that that charge is nothing but surface charge. Okay, surface charge, and that charge can be, you know, spread over infinite width and infinite height. So it is not you know, advisable or practical to always measure that charge and then find out the effects of that charge. Rather, for that we define a quantity rho s, which is nothing but surface charge density. Similarly, if a charge is in the form of cluster, either a continuous cluster or, you know, scattered point charges here and there, okay, which occupy a certain volume, in that case that charge distribution, that source distribution in other words, would be classified as the 3-dimensional source distribution. And for that we say that this is a volume charge distribution or volumetric charge distribution, and for that we again don't use the coulombs as the unit of charge. Rather, we don't take that charge as it is. Rather, we try to classify the effects of this charge or this charge distribution or this charge distribution in terms of we try to classify that distribution in terms of density. All right, so this is line charge density, surface charge density, and volume charge density. So you should expect that line charge density, since we are talking about density and it is only in one dimensions, should have units in coulombs per meter. Okay, and surface charge density, since we have got charge distribution in two dimensions, so charge per unit area. And for three dimensions, the charge distribution, that is the volumetric charge density, since we are talking about density in three dimensions, so charge density, volume density, meaning we should divide that charge by the volume. When we will discuss those distributions, we'll we'll mathematically define these things, so never mind. But you should always remember that only zero dimensional charge distribution, that is a point charge, is always measured in coulombs, and we take that as coulomb point charge and try to find the effects of the source. But when the charge distribution is other than zero dimensional, or if the charge distribution is other than a point charge, that is if there is a line charge arrangement or surface charge arrangement or volumetric charge arrangement, in that cases, since these arrangement can go up to infinity, so the charge on those arrangements, if summed up together, would end up in an infinite charge. So it is impractical and unadvisable to take the whole charge and try to find out the whole infinite charge and try to somehow cram it and get some effects out of it. But that this is not possible mathematically. So what we do, we rather, instead of taking the whole charge, we take the charge densities. All right, so what effects can we find in all of these four distributions? Number one effect will be the electric field, okay, which is a vector effect, and electric flux, which is a vector effect again for zero dimensional distribution. Also electric field intensity and electric flux density, electric field intensity, electric flux density for all the four charge distributions. Okay, these are the effects which we'll try to find, and we will try to quantify, give it some mathematical form. And the other thing which we will try to find out would be potential energy. Okay, potential energy, if a point charge is located surrounding if this is the source, there should be some effect surrounding this source. So the effect, the scalar effect of that source which we would be interested in would be potential energy. All right, same is the case with this one, same is the case with this one, same is the case with this one. So it means that we will try to be as comprehensive as possible in our study of electrostatics and magnetostatics. We will try to find out the electric field intensity of all the possible charge distributions, and we'll try to find out the electric flux density of all the possible charge distributions, and we will try to find out the scalar effect of all the possible charge distributions, and that scalar effect is going to be potential energy. So notice that this, if I categorize further within this category of vector effects, the first effect, which is the electric field effect, belongs to the force field type of vector effects, if you could recall the lectures of week 1. Okay, and the electric flux density belongs to the flux density type of vector effects, flux density in which there was some flux density type of vector effects, the effects in which some sense of movement was present. Remember that? So when we'll discuss this, we will talk about that sense of movement, inshallah. And the vector effects, the force field vector effects, which we discussed in week 1, were the effects in which there was no sense of displacement or movement, but there was a sense of force, all right, everywhere in that field. So this category belongs to force field type of vector effects, and this category belongs to flux density type of vector effects, and this category belongs to scalar effects of the stationary field of these sources, which forms the electrostatic field. And not only we will discuss that source, but also all possible combinations of all possible arrangements of that source will be discussed. So magnetostatics now. So magnetostatics has got I have not written over here the source of magnetic field, you already know. So here we have there is no concept of we said that if charge is moving, so let's why not write it over here. The source of magnetostatic field is charge, moving charge, number 1. Okay, moving with constant velocity. Velocity is important. We are not interested in speed. And constant in magnitude. Okay, constant in magnitude. This sort of charge would produce electrostatic field, or would be the source of electrostatic field, and that source can be present in the form of in any form, but all those forms can be classified into either one-dimensional distribution of source, two-dimensional distribution of source, or three-dimensional distribution of force. So one-dimensional distribution of force is filamentary current. I don't have a space, so I'm just writing it, filamentary current. Filamentary current is nothing but if we have got a conductor and a constant DC current is flowing through it, all right, and the radius of this, if we take of this conductor, cylindrical conductor, solid cylindrical conductor, copper का ये wire हो सकता है, if we make the radius approach to 0, so that cylinder would convert into a filament. Okay, the current flowing through that filament is filamentary current, and that current distribution is one-dimensional distribution. Obviously there is no concept of zero-dimensional current. Okay, that concept is present, but we are not discussing it here right now. All right, so second is surface currents which flow in on the surface of a conductor, or a plane conductor, or a circular conductor. All right, there is no depth in that current, they are just flowing over the surface. All right, that very usually happens when we discuss the high frequency cases in which there is a skin effect. All the current which should be distributed throughout the cross section of a wire, if this is the wire and a DC current is flowing through it, so the charge distribution throughout the cross section would be same if the current is DC. But if you introduce some frequency in that current, so and let's say that frequency is very high, then the current distribution, the charge distribution will not be uniform. The charge will be pushed towards the skin, and if you are at the edge of the frequency where there is no antenna effect, if we are working on very high frequency where this conductor is not becoming an antenna, where when there is no radiation, so in that case, you know, the charge will be on the surface of the conductor. All right, so normally filamentary conductor is one dimensional, all right, and surface currents is two dimensional, and we have got volumetric currents, you know, that normally happens if we flow a current, direct DC current through a cylindrical conductor whose radius is not equal to 0. So in that case, again, in all these three distributions, we will try to we will discuss the scalar effects and vector effects, and in vector effect we will discuss firstly magnetic field intensity for all the three cases, and then magnetic flux density, inshallah, for all the three cases, and then we will try to find the magnetic potential energy or magnetic potential fields for all the three cases. And here you can classify, you can subclassify, as was the case here. This magnetic field intensity belongs to the force field type of vector field, and magnetic flux density belongs to the. So we will try to be as comprehensive as possible in the studies of electrostatics and magnetostatics. और अगर हम engineering level के ऊपर आके comprehensive नहीं होंगे तो फिर कहाँ पर होंगे जाके. All right, so we will discuss all the cases inshallah. So that's it for today, and from week 5 we are going to start our electrostatics. These two tables should be at hand and should be handy, and you should always keep them with you so that you can figure out where we are and why we are studying which topic. Okay, so keep these maps in your at hand and also in your mind, and inshallah we'll start formally from next week at the portion of electrostatics, and then we'll move on to magnetostatics inshallah. So till then, assalamu alaikum.